I guess we should probably move on to keep the schedule, right?
Mm-hmm. Yeah, we have now the final part of our workshop, which is the panel discussion. I would like to invite all the speakers and presenters from papers to participate. If you can switch on your camera so that we can see your pretty faces, and feel free to interact. Maybe as a, let's say, as final question for Michelle, and maybe first question for the panel, because many of the participants have similar concepts, and then we can go maybe to more general questions about action representations. But I would like to bring this question out that is in the Q&A that says, the topic on desired motions on action spaces, if you have the generator G creating entire trajectories, what would be the advantage of learning a policy pi instead of using a low-level controller to move to the next state? So I think there are several works that also output directly a trajectory, for example, some of the papers that were presented, and also different talks presented ideas of having a low-level controller that can be learned or not learned, including our own work. So I think that would be a good question to start with for Michelle and any other participant that would like to give his or her opinion on why using that instead of just directly a policy pi at the low-level control.
Yeah, okay, so I guess from my perspective, the policy can be basically a compiled version of model predictive control. You can't beat the speed of a directly learned policies. That's one comment. And then another thing is that at least for locomotion, different types of motions need different amounts of anticipation and look ahead. And so that's something also that the policy can choose to focus its attention on. And whereas, and you know, I think you can build some of that into model predictive control as well. But that's something that, just by treating it as a very local inverse dynamics problem, that you're never going to get that anticipation that you do really need to do some slightly longer time horizon tasks. Yeah, I'd love to hear what others think more in terms of manipulation, etc.
Maybe then I jump in. Maybe Jeanette also wanted to. I think Roberto, your last question was like really, really good. And to me, it was less about like timescales, as Mikael kind of answered, but much more about interaction with the world, right? Mm-hmm. And this is one thing also for myself. I mean, in the earlier part of my career, I wouldn't have considered myself as being a roboticist. And it took a while to understand what it means to be a roboticist when you actually start trying to understand what it means to interact with the world, right? It's so different to just reasoning about the trajectory in some, configuration space. Well, unless you include the full world in that configuration space. And so, so that's why I really appreciated actually your question. So in this sense, I think like many of the things that we are very strong with, when it's only about motion and only about trajectories, and also, and this includes model predictive control, we really have not yet understood when it is about interacting with the world and how to represent these kinds of actions. And yeah, that's just my point. Maybe other roboticists, real ones, can actually pick up.
Maybe let me just throw in a thought that sort of dwelled over the last couple of discussions, and that is that distinction between the high-level control policy and lower levels. And coming from humans, and what people have conjectured and shown over many years, is that distinction between levels, I think, is a changing one, to the extent that it's very top-heavy in the beginning, and then when you learn a particular skill then it seems to get pushed down into lower levels of the nervous system. And so if I sort of project this neuroscience notion onto the controllers that you've been discussing, it would kind of mean that the higher level policy fades away, gives rise or puts all the power into the lower levels, which partly makes it then less flexible and or needs to elicit the insertion of higher levels again. So what I just wanted to throw in is the fluidity of that hierarchical distinction that seems to be recognized in human control, not fully, it's thoughts, but I just wanted to sort of bounce it into the discussion for you. I guess
This is actually very, very nice. So in other words, maybe from robotics perspective, the more grounded, higher level abilities we have, the better our systems would get, right? Because this line between the two levels, the high level and the sensory motor low level, will be very fuzzy or moving actually. The more elaborated these higher level skills learned in whatever simulations and higher level descriptions, which are not very, very tightly coupled to the word and don't have understanding actually of what interaction with the word means, the more elaborated and grounded these high level concepts, the better is our control or our system in general.
Yeah, I mean, I think incrementally free up higher levels, relegate certain components to lower levels in order to then to turn to the next skill.
Is this a problem of, is this a biological problem? Let's say that we don't, maybe I'm just throwing here, we don't need to solve on artificial systems. It's just a problem of limited cognitive attention ability. And that's why we outsource, when we learn how to do a task, we kind of like outsource from whatever part, I'm not cognitive scientist, whatever part of the brain that is more of the front of the attention and goes more into an automatic process. And I don't know if we have the same benefit or the same need on robotics. We also have computational limitations, but I don't know if it's biologically really the same in terms of having just one process that is kind of like paying the attention. You cannot multitask so well as a computer could actually multitask in a much more efficient way. So I'm not sure. I'm just thinking aloud.
Yeah, but I mean, it could, while of course it seems to be more unlimited in the artificial systems, the computational power. It may nevertheless leverage the ability to more multitask while it's possible, but to have these lower level actions just flowing away and then turning to new tasks.
Mm-hmm.
I think compared to robotic systems, humans in all those dimensions of speed and capacity seem to be so disadvantaged. Nevertheless, right? Nevertheless, we're still better. So it's an attempt to maybe see where are humans smarter. That ultimately leads to their better adaptability, learnability, etc.
I'm trying to map what Dagmar is saying right now into my world, and I'm struggling a little bit. So I'm not sure I'm mapping it correctly. But are you saying that at the higher level, as we get better at the higher level, we are starting to learn policies that are reactive at the lower level that we can just reuse over and over, or like? Where is this kind of what you're saying? Or
yeah. So it started, when you and then Jeanette were talking about your distinction of the controller and the policy, that that this shouldn't be a static distinction, an unchanging distinction. And yes, so when the lower levels are properly engaged, when primitives are adapted to the task at hand, then you disengage the higher level to turn to other things or save energy.
Okay. That makes sense to me.
So I have a question. How many levels are we talking about? So we talk about low and high level, but there's no, I think as far as I understand, but maybe Dagmar, you can correct me, that the human brain, we don't have high and low level, right? We have tons of different loops with tons of different timescales.
Yes.
So how does it translate in robotics? What does it mean?
Maybe to add on this, so when I was listening to this, I hope it's not destructive to say that, I was wondering, do we have any clue what we were talking about when we talk about high level and low level all the time? And now maybe even counting levels, right? So maybe this is, I'm improvising this, maybe this is not the right way to think that we have these rigid levels. We've been thinking this for so long and developed all these things of options and hierarchical reinforced learning and hierarchical control and things. Maybe that's not the right thing. Maybe what we need is something completely different to think about, not levels, more like a new Rodney Brooks kind of view where like everything would have to span all levels. Like you always, I would say you always formulate the problem jointly over everything. And all the things that I established, they always cover everything. But then some of these just become burned in. So maybe they're trained and so you really learn the heuristics that you don't need any actual reasoning or computation anymore. And some of them are not burned in and you still have to do some cognitive load things.
I think we sort of got stuck into that very simple hierarchy, higher and lower, which is totally simplistic, of course.
Yeah.
And so there's very likely to be multiple levels and there's very likely up and down connections. And then once we start to allow for that, we're basically in a network, a level multi-connected network view. So how could that be a thought to change the controllers for the robots? And certainly just to say just one thing for Ludo's question. I mean, the brain is, yes, there is multiple subsystems, and I don't think there is a strict hierarchy in the sense of lower and so, okay, how can that potentially influence your controller?
I want to tag on.
There are.
Oh, sorry, Tamin, or who was it?
Sorry, yeah, but there are hierarchies in representations, right?
Are there?
I don't know. I mean, there's an entire conference on representation learning, and maybe people in this workshop know more about that. At least in vision, you know, the classical vision approach is how we learned that you have features, you group them together, and so on, and you have hierarchical representations of perception or perceptual features.
But then came deep learning and just was throwing all of this, apart, right?
This will disappear.
And now they call themselves, representations, but maybe they're not, strictly hierarchical anymore.
No, but our understanding of things is hierarchical, actually, right? No? I don't know.
I want to change the direction into more what Dagmar started to talk about was, I think we need to think about what we want to communicate between these different, let's call it modules or layers or whatever, because there are usually these bidirectional communication channels in our brain, and maybe that also then changes the thought about this being a hierarchy more like versus it being a connected net of things that communicate together. But I do think it's an interesting question to think about what should be communicated between these layers.
Yeah, I mean,
sorry.
Go ahead.
No, I mean, I think so. Francie has maybe pointed, and maybe to Mark as well, is let's assume every layer solves a mathematical program, right? We tend to think about those things sequentially, but these things should be concurrent. And then the notion of timescale and how these actually synchronize or talk to each other. How do we think about it, right? I think this hierarchical view that first I do this, and then I do that, and then I do this, and then I can send it to the robot. And I guess Jeanette will not disagree with me, is not the right way, right? It's just that I don't know how to think about it in a different way. I don't know if anyone has an idea how to do that.
My one thought related to Dagmar's comment is that the levels often need to communicate when things stop, when things are or are not going according to plan. And and this is also just something from introspection. Somehow I feel that when we as humans are doing motions, we know whether something is going according to plan or not. And if it's going according to plan, we don't pay any attention. So there's Dagmar's kind of push down to some autonomous thing. You know, I'm driving or doing whatever, things are going well. And then suddenly, you know, you feel, I don't know, maybe you feel something that's suddenly on your hand that's totally unexpected. And then, you know, anyhow, so I do think that might be some notion that's missing in many of our current models is some notion of expectation and some notion of when a controller is just truly going out of distribution and is just doing something unexpected. Prediction and uncertainty and knowing when you're out of distribution is, I think, an area that still needs a lot more work.
Yeah, I wanted to add to this topic maybe the problem and why we are kind of like stuck or not stuck into this hierarchy thing is just historically and kind of like we have computer vision that is kind of like the high level that will tell the low level, which is control theory, what to do. And because we have this kind of like well-defined, established, and kind of like successful fields in robotics, we say, okay, let's kind of like put them together. But I completely agree that this in a complex interactive system, what is more intuitive is that there are several processes that are at the same time, several processes of different time scales, several processes that are kind of like concurrent. I guess it's just much simpler to analyze and control a process that is sequential than several concurrent processes, because just trying to get stable such a system becomes really, really hard. So I guess that's also a reason we try to tend to kind of like process sequentially and analyze problems in a sequential manner. But it's true what Mark says, that maybe to solve a task, we should not think of these levels, but rather subsumption architecture and having this different full stack from high to low processes working in parallel.
Can I just say a comment about the easier to handle sequential structure? And sequencing and serial order is one of the primary things in speech production, right? And which is a highly complex articulatory system. And we're forming all these sounds with our gestural apparatus. And in speech production, one of the primary pieces of facts is that there is mutual interaction across across elements. So the images, it's not beads on a string, but there is hereditary and anticipatory effects. And that doesn't only go over successive elements, but over more than successive ones. You prepare vowels in order for the next consonant, etc. So just as we are discussing softening the hierarchical structure, I don't think the sequential structure is as rigid as one might, at least first order, think.
Animus, go ahead. I think you have your hand raised.
Yes.
This was wonderful. Thank you for all of the speakers. I have this question, and this question goes back to a comment that both Tamim and Mark made. Don't we think hierarchically, and why should we not model it hierarchically? I have one comment and a question. The comment is, I think that was the bane of vision, that because we felt we think hierarchically, we hand designed such hierarchical systems, and all of the new learning-based systems clearly still are principally hierarchical. It's just that hierarchies are not hand designed. Now, the question part is, how do we do this for control? And this is something that me and Roberto have been thinking for some time now, is how do we come up with these hierarchies of control, but that are not hand tuned? So Franzi basically gave this example where we can have task spaces as one potential example. A very good example that Michelle had was basically that these task spaces are not actually stable or stationary, right? In the sense that I'm not always operating in end effector space. Maybe depending on the tasks, let's say stability of control, it will change, right? Maybe I'm riding a bike and I'm operating only about the handle and the center of mass, but as it goes on slippery road, I think slightly harder. And how do I do this dynamically, and how do I learn these hierarchies without explicitly specifying what the hierarchy should be, both in task and motion planning, the kind of stuff that Mark has showed, and also in just choosing task spaces?
I think in control, it's easy, right? The hierarchies are given by the timing, but maybe Ludwig can elaborate on that. Right?
No, I mean, I think maybe it goes also towards what Mark was discussing earlier, is physics gives you timescales. And I think this idea of physics simulation goes exactly into these things, right? For different timescales, you use different types of physical models and different types of things. And that might actually decide where is the decision-making process going, right? Because it's imposed by the timescales of the physics to some extent. How you come up with that, I don't know, but I would imagine that it should exist, right? And there should be.
Yeah, I think in control, we already have these hierarchies actually, which is given by the time scale of your controllers, no?
Yeah, gravity tells you how fast you need to decide where to step, right? And that's a given, right? You don't have, there's no need to figure this out, right? It's given by the equations of motion.
We have a question from the audience. Where does embodied intelligence or mechanical intelligence come into place across these layers or low-level, high-level idea of control approaches, both in human studies and in robotics? In other words, where in the computation does the system take advantage of its internal dynamics to simplify the task?
Yeah, this is a very good question. So, and I think maybe this is something which is missing in all these levels and hierarchies. I wouldn't call it now low and high level. We can call that left and right level, but there is something in between. And from my perspective, I think these are really what's happening in memories. I don't know, that all these processes, what are needed, should happen somewhere, and it doesn't really happen through the just drawing arrows between different levels, but these are loops actually in different kinds of memories, again on different levels of time scales and maybe hierarchies of representations. And I think this is crucial, and this is where you can actually link these two levels, the symbolic and sub-symbolic representations, through processes at different time scales, different levels of abstractions. And this is where we don't know actually too much about how these things should be implemented. So how can you, what kind of approaches are needed in order to extract abstract representations from sensorimotor data and vice versa, to map high-level abstract whatever plans to controllers at 1 kilohertz or 10 kilohertz frequency. And so this is just, I mean, of course, some people in robotics, they implement kind of memories, which is nothing more than a database where you put data, but not really this deep understanding of the different types of memories and the different types of how maybe knowledge should be represented or stored, retrieved in a very efficient way in these memories. Okay.
Can I
Mark?
just throw in sort of a very, oh, somebody else?
Yes, go ahead. No, Mark and Francisca have their virtual hand raised. So maybe go ahead, Dagmar, and then we can have Mark and then Francisca.
Yeah, so to the question, where is embodied intelligence, physical intelligence coming into it? And I love the question, and I would love to say something factual about it. And I feel I'm trying in my work, but I can't present anything yet. And sort of the bigger view on things, I think that has been coming, that question has been coming over the past 20 years or 30 maybe, in psychology, philosophy, as much as also in robotics, partly driven, I think, through soft robotics, where you have underactuated dynamics that you want to exploit. So in human movement science, it has really been shut out originally because it was sort of coming from psychology, and psychologists couldn't handle much more than a finger and sort of explicitly eliminating any mechanics that would complicate matters and deflect from what's really interesting in the brain. And then, say for the last 20 years or something, control theory has been imported into human neuroscience, but in very simple ways, again, on very simple tasks, reaching and stuff like that, where that embodied intelligence just doesn't have a chance to come out. So it's been really researched away, that very exciting question. And I mean, me personally, I absolutely want to go there with big movements where this actually plays high. But I say something insulting now. So in all collaborative fashion, I think it's partly control theory that has, in its basic fashion, that has not asked the question, and human neuroscience has looked at control theory as the holy grail where all the answers are, where we answer those control questions. So I think it is up to you guys to become more richer in understanding how this physical intelligence can be leveraged for more complex tasks, and then we happily tag along here in the human movement world.
Right, thank you. Okay, Mark, and then Francisca.
Right, so I was actually raising hand since Animesh was asking the question how to learn hierarchies, but I decided that my answer is also an answer to the other question about embodiment at the same time. And the answer is by formulating the problems jointly and holistically. So let me elaborate on that. I think, so my PhD students, I sometimes say that these machine learning or pure machine learning researchers, they have a much easier job because they kind of know what they're doing. They can formulate, they know how to formulate the problems. Same with computer vision. They have a much easier job because they know how to formulate the problems. They can write down errors, things, and maybe also in computer graphics or so. They know how to formulate the problems. And then, and maybe also, Dagmar talking about language and language generation. Initially, people thought that they would need grammars and anything to understand language, right? But at some point, they said, no, let's just write down an objective, one machine translation, and all of the things just, came out from there and kind of developed from there. So in that sense, my answer to Anime's question would be, if we just manage to really formulate the problems of robotics holistically, then necessarily the solution will develop the hierarchies if they need them, and if not, then not. If we just can formulate it holistically, and a bit the same then also to embodiment and also exploiting environmental constraints or dynamics or so. I think it's almost the same thing. If we only formulate the problems for only a part of it, like only the control part, then we skip out and miss to actually also include the formalization of the actual dynamics and the robot and the environment. But only if we actually can formalize the thing holistically, then the methods will also automatically do, you know, embodiment and exploiting dynamics and soft robotics and everything.
I do have one comment. I really like Mark's argument that we have to have a sort of holistic argument where the objective is true performance, nothing else, kind of thing. But hierarchy or emergence of hierarchy is often a feature of the inductive bias of the model, not necessarily just the objective. A very sort of like naive or maybe even toyish example can be, I can write a classifier as MLP versus a CNN. MLP would have the same objective but not solve the problem, but CNN would have a slightly different inductive bias and learn the hierarchies to solve the problem. So there still exists a question of what are those inductive biases such that I don't have to design the intermediate argument, even though I still have the same objective.
Like, just a really quick answer. I totally agree, but I think the objective should be there first. Like our understanding of the actual problem should be there first. And then, and not the other way around, that we first think about how can we do software engineering and hierarchies and whatever, and then stick things together.
So we are just 15 to 20 years behind vision people. We'll get there. Thanks.
I just wanted to mention that I connect this question of embodied AI to this topic of body schemas that we actually do have in robotics, right? The field of body schemas is busy with learning internal models of the robot itself, but also how that these body schemas are extended when we're interacting with tools. And that's, to me, how all the layers then are also connected, because these body schemas are operating at different levels. They do have kinematic features, but they also should be having dynamic features. They're centered on the robot that is manipulating the world, basically. And that's, to me, how embodied AI can be, you know, captured.
Maybe we can try to cover one more question from the audience. The question is, from a neuroscience perspective, is learning a skill at one level the equivalent of developing instinct for some motion? And this enables you to think at another level once you develop the instinct for other motions. So I guess maybe the question was on the, once you develop those instincts, then you can use that for learning on another level, on a higher level, I assume.
I can briefly pitch in on this. I think there's part of this relates a little bit to there's you know, system 1 versus system 2 that is being pitched by various communities, and that basically says, okay, system 2 is a reactive learning, or being able to make reactive predictions, and so a typical neural net policy is just a straight reaction from state to action. Whereas when you're trying to plan, then you need to do some kind of explicit search, and that's more slow and painful and requires explicitly considering various options. And so yeah, I do think that well, I partly buy into the fact that when you've done enough, the more experience you get at solving problems using explicit search, then eventually you develop a template, and you turn it into a pattern recognition problem that says, oh, okay, you know, in the context of kind of Mark's manipulation world, you know, if there's an object far away on the table, you know, at some point I might reflexively think, okay, I need to find a stick or some big object I can use to drag it towards me. And so, yeah, so I do think that that there is this kind of compilation happening of sorts.
We have Francisca raise hand. I don't know if it's from before or not. And then we have Tamin that has a question.
Mark.
Okay, that raise was from before. Okay, Tamin, go ahead.
Yeah, actually, I have a question to Mark. Yeah, very, very nice presentation. So you made two statements. So one, you said, okay, for the path optimization problem with all the math here, you said that details are not important, right? Or was that for the explanation, or was that details about the problem? I hope just for the explanation during the talk.
I'm not sure what I said, but definitely I would say if I said details are not important, then that's false.
Okay, so and then you mentioned that this tool or the new formulation is a tool for you to generate data, right?
Yeah, that's one of the things that we get out of it. Yes.
Okay, why actually do you think we don't have other tools to generate data, or what would be better, or why is your tool better now than, for example, simulation frameworks with which you can generate also data?
Oh, but this data is expert data, right? So this data is data about here's a scene and some random task that you might want to achieve in the scene. And it's even very interesting to define random generators of tasks actually to achieve in the scene. And then, well, we call a planner, and that is quite computationally heavy. And then we get actually a plan that is an optimistic guess of what would be possible to achieve that. And so this is expert data. So it's completely different to just sampling data from simulation. Right? It's
I didn't get it.
We also
actually
used it as for supervised learning, actually, to learn these deep visual heuristics, for instance. And it's a complete game changer if you have a data generation mechanism that actually really generates data for supervised training versus just a simulator where you have to explore. So in that sense, this thing actually explores completely different, strategies. For instance, all of these different pushing strategies with the stick, how the stick pushes the box. How would you ever sample that otherwise from a simulator, just randomly? So.
And why do you call it expert data? Sorry, again.
Because it's the result of some planning, and it's not.
But I can generate any scene in a simulator and use a planner, to generate also data, right?
Cool. Which planner will you use?
So the planner is the expert for you.
Yes.
Oh, okay. And your vector actually is a 6D range vector or only 3D?
It's
for
6D.
Contact 6D. So
Yeah,
this means you can deal also with non-rigid objects, right? Because you are modeling forces and torques at contact points. So more or less you are assuming soft contacts.
No. No. Okay, it's representing the wrench exchange between two rigid, but this is now super technical. I don't know if this is the right place. It's representing the wrench exchange between two rigid bodies. And the wrench exchange is by default exchanged by a single zero moment point of contact. Okay. And there is nothing about software or anything like that.
Okay.
You should do this offline with a beer, Tommy.
Okay, then we do it offline.
So I have a question from the Slido that I would like to hear your opinion for, and maybe wrap up with that. So we have seen that there are many different action spaces or different ways of representing the problems, both in robotics and neuroscience. So one question there is, do we know if there are best action spaces for certain tasks, or is always going to be more of a trial and error? Or is something that we can, in a mark way, can we put that as part of the problem maybe, and the definition of the problem to try to find the best action representation for the task as well. Do you guys have some thoughts on that, or do you think it's too early to know what is the best action space or action representation for robotic tasks?
Can I chime in without raising my hand?
Yes, go ahead.
So I think while I was using a slightly different language, I called all the spaces that I had, I called them solution spaces, which I think maps onto what you think is action space. I actually, in humans, we don't know what is controlled. We don't know what is the target of control. And so in my talk and my work, I'm trying to use that instrument to find the most fitting action space to the data that I have. Because specifically in this complex object interaction, continuous complex object interaction, if you want to start to look at learning, well, okay, there always is an error and the error goes down, sure, but you don't learn much, right? Because you know what's going to happen. There's an error and the error goes down with practice. So how can you learn what else other than this very superficial error criterion is actually target of control? And so what I was trying to do is to develop that instrument of creating different action spaces to then compare with the data to see that space or another space is the appropriate one to capture the data.
We had one more question. I don't know if we have time. Shabbat had his hand.
Yeah, if you have time. Yeah, I have a question for Mark. So if you want to do something in the real world, what would be your ideal overall solution be?
Did you say RL, like reinforcement learning?
No, if you want to do a particular complex task in the real world. So how do you see the overall solution from what you talked about today?
Yeah,
overall, I think.
The overall, okay, thank you. Didn't get that. Why I cannot
How do you
answer
solve
this.
robotics, Mark?
Don't know. No, I really don't. I really don't know. I mean, by this work that I've been doing so far, it was just me, learning things. It was like an exercise, like some homework for me to learn more about, what is the implicit structure of doing sequential manipulation planning only, right? And now with the whole team, my poor students and my poor postdocs, we're like really, really discussing hard of how to transfer these kind of skills into the real world. And I think the current state of our internal discussion in the team is that it doesn't make sense to believe too much into that these trajectories can be literally translated, right? But I firmly believe a lot that these kind of reasoning mechanisms and trajectories are heuristics, again, in the AI sense, and they are optimistic estimates of what is possible. And I more and more think that these optimistic estimates of what is possible are actually a really, really good guide to then really design the controllers or maybe really train the controllers. And now I even said the word already, guide.
Okay, okay.
Pretty much to guided policy searches, all right? So yeah, but we don't know.
Okay, thanks.
All right, so I think we're at the end of the workshop, unless there is a very, very pressing question that needs to be asked right now. If not, I would like to thank everyone, so especially our speakers, our poster spotlight presentations, and everyone attending the workshop. And I hope you enjoyed the discussions, enjoyed the talks, and yeah, think a little bit more about what action space is good for your robotics problem, or how can you actually make it part of your solution. And yeah, enjoy the rest of the conference. Thank you.
Thanks, Roberto.
Thank you, Roberto. Thank you for.
Thanks, everyone. Thank you.
Bye-bye. Bye.
Thanks, everyone.
Bye.
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 Thank you.
Hi.